Here we will see an interesting inversion of the double slider linkage. The linkage is shown here in a schematic form. So it has essentially 4 links and 4 pairs. 2 of them are revolute pairs and 2 are sliders. Now we are going to fix link number 3 like this. That makes link 2 and link 4 as the input and output links. And since they are connected to the fixed link through these 2 pins which are capable of complete rotation, both 2 and 4 will rotate completely. Finally, link 1 is connected to link 2 and 4 via these 2 prismatic or sliding pairs. Now the geometry of sliding pairs is such that the guide and the slider are aligned with each other. So if the guide turns through a certain angle, the slider is bound to turn through the same angle. And if the slider turns through a certain angle, the guide will turn through the same angle. In effect, if we give some rotation to link number 2, it gets transferred to link number 1 as it is. Same direction, same magnitude. And link 1's rotation will be transferred to link 4 as it is. So the net effect is, if link 2 turns through some angle, link 4 will also turn through exactly the same angle. Now let us see this mechanism in a more descriptive form over here. So these 2 fully rotating pins B and C are over here. And connected to them are link 4 and link 2, these 2 links which will fully rotate. And link 1 is this orange link looking like this cross slot, is engaging with both link 2 and 4. Let's watch its motion. So I will drag on link 2, our input, and you can see link 1 undergoes the same rotation, and that rotation gets transferred to link 4 as it is. So in effect, link 2 and 4 both are rotating through the same angle. Now where can such motion be used? Well, you can notice the axis of rotation of B and C are parallel to each other. So if we want to transfer the rotation of this axis to the other, so 2 parallel shafts you can imagine, then this will be a very useful mechanism. When used for this purpose, that is for transferring rotation of one shaft to a parallel shaft, this mechanism is called as Oldham's coupling because it couples those 2 parallel shafts. Now let us see the physical arrangement which will help us do that. So link 2 and 4 are 2 shafts. Say link 2 is our input shaft shown in green here, link 4 is the output shaft shown in yellow. And at the end of both these shafts we have these discs or flanges, and in each of these flange we have a slot dug. Okay, so there is a slot here and there is a slot here. Link 1, which is this red disc now, has a mating projection that engages in these slots, and you can notice these 2 projections are at right angle to each other. Let us use this action link here to see this in 3D and watch the animation. So this is how Oldham's coupling looks. This is one shaft, this is the other shaft, and engaging with both of them is this intermediate disc, our link number 1. If you see in this view, you can notice that the 2 shafts are not collinear, but they are parallel. So there is a little offset between these 2 shafts, and that is precisely why we need to couple them using this special coupling, the Oldham's coupling. Let's set this in motion. So this is how Oldham's coupling moves.